Yeah, let's talk about how we implemented zero-copy IPC in Dora. So we first focus again a bit on Dora inputs and outputs, and then look into message passing using shared memory. So we focus on the general design and show how we implemented automatic cleanup of shared memory messages. And then we talk a bit about possible optimizations and also opportunities for future optimizations. In the second part of this talk, we'll talk about zero copy between Rust and Python and how the arrow format that we already heard about today is going to help with that. And also it's going to help with implementing higher level types or higher level messages using higher level types. So in Dora, we have a data flow that consists of multiple nodes, and they communicate by sending messages to each other. Each node here is a separate process which has advantages such as isolation, so a crashing node doesn't bring down all the other nodes. And we have scheduling fairness because the operating system can schedule the different nodes individually. And we also have kind of flexibility because the node authors can have full control over their process, so there's not some framework that they need to fit in. As a side note, we also have a concept of operators in Dora, which is a way to let multiple nodes in a graph share the same process. But in this talk, we're going to focus on the nodes and not the operators. So as I said, nodes communicate through messages, and we implemented it in a way that each node defines a set of inputs and outputs, and you use a data flow YAML file to map the two together. So here we have an example node that has some output, and node 2 is going to map that output to an input called foo. So this way Dora can forward the message to the correct receiver. So when talking about message passing, there are different ways that we can do that across process boundaries. So the obvious choice or simple choice is using TCP sockets, which is supported on a lot of platforms, even some embedded platforms supported, and Linux, Windows, and so on supported very well because that's like how the internet works, right? So you can contact local machines, you can also interact with remote machines, so this allows you to split your data flow across multiple machines and use everything together. The drawback of TCP is that it can be relatively slow for local communication because we have additional overhead because of acknowledgements, and we need to copy the data in order to send it over the socket. And also we have some metadata that is typically that is used for addressing remote machines that we don't really need for local communication. So for local communication, we could, for example, use Unix-specific IPC, which is not available on Windows, unfortunately, but it's much faster than TCP sockets. So some examples are domain sockets or pipes or message queues. But this only works on a single machine and it only works on Unix systems. So it's not a good fit for Dora, where we try to be multi-platform. And finally, shared memory. Shared memory is also quite portable. It works on Windows and Unix systems. And it's even faster than the Unix-specific IPC implementations because it avoids copying the data completely. So we have a single memory region where the data lives, and both processes access the same memory region, so the data doesn't need to be copied at all. Like the Unix-specific IPC, it's only working on a single machine, so we need a backup solution for addressing remote machines. So in Dora, we decided to use TCP for remote machines and shared memory for local communication. Shared memory works quite similarly on Unix systems and Windows systems. It's based on file descriptors. So on Unix, you first create a shared memory file descriptor using shared memory open. Using this call, you specify some unique ID. And then you can map that file descriptor into your process's address space. And then you can share that ID with a different process, and that one can also map it and access the same data. The allocation works by first unmapping the memory from your address space and then unlinking this shared memory file descriptor. On Windows, it's a bit different, but kind of similar. So you create a temporary file, you use the normal file creation API, but you set the share mode option, and then you use either the create file mapping or open file mapping call to map it into your address space. And for deallocation, you call close handle on this shared memory handle. Fortunately, we don't really have to deal with all these operating system specific details because there's a shared memory crate on crates.io that abstracts over all these details and provides a cross-platform API for using shared memory. So as a simple example, we have two processes. In process A, we create a new shared memory region with size 4K. And then we use an unsafe raw pointer to write some data to it. After writing the data, we can get the operating system ID of that file descriptor and send it to the other process. And in the second process, we can then read it, use it to open the very same shared memory region and read the data out using raw pointers again. We have to use raw pointers in Rust here because the Rust compiler cannot understand what's happening here. So you don't have any of the safety requirements or guarantees of Rust. So you have to make sure yourself that you're not creating any undefined behavior, for example, by doing data races or use after free or something. So it's a bit difficult to use, but it's possible to wrap this in a safe API that you can then use more conveniently. For passing data using shared memory, we first need to prepare the message in the sender. So for that, we first need to know how big the message is going to be when serialized. One approach for that, one easy approach, is to serialize it to a byte vector first, and then we can check the length of the byte vector. But now we need to do an additional copy because we just serialized it to the heap, and then we need to copy it to the shared memory. So this approach is not really a good one. So it's better to use a recursive approach, and basically the idea is that for self-contained types, we can just take the size of the type. And for types that contain pointer data, in addition, we need to sum up all children, like everything that is referenced and lives somewhere else. And then we know the size of the shared memory region that we need, and then we can do the actual allocation. And after doing the allocation, we of course need to copy the data in. Unfortunately, we cannot really avoid this copy because this shared memory region didn't really exist before. But what we can do is to avoid any additional copy beforehand. So we can try to construct the data directly into that shared memory region. So for example, instead of serializing to the heap first, we serialize directly into the shared memory to avoid copying the data, which can be important, especially if it's large data. After preparing the message, we can send it to receivers. And as we saw, this works by sending just the ID of the shared memory region to the receiver. And since we need to somehow cross the process boundary, we need to use an IPC channel for that as well. So for example, a TCP channel. The throughput of that channel is not that relevant because it's just a few bytes of data, it's just a string. But the latency is kind of important. So when we're using TCP, then we should configure it that it should not wait for acknowledgements and so on. And maybe it's even better to use a different communication channel with lower latency in the future. Yeah, and in addition to the shared memory ID, we might also want to include some additional metadata, such as the ID of the source node or the ID of the output, which helps in routing the message to the correct receivers without inspecting the data. And in general, it's possible to send a message to multiple receivers, so they all can map the same shared memory region. After receiving a message, the receiver can map that region into its own address space, and it's important that it does this in a read-only way to prevent accidental modification, because there might be multiple receivers and modification of the data might lead to data races and undefined behavior then. And after mapping the data, we can copy it out, or more efficiently, we can perform some operations directly on that data. And ideally, we write the result directly to a new shared memory region. So for example, on the right side here, we have an add operator that reads the input from two image inputs from two different operators or nodes. adds them together and writes the result directly into an output shared memory region. This way we don't have any intermediate copies and can work with very large data without additional overhead. Yeah, the question is, how do we do deallocation? So because we did a manual allocation, we need to do a manual deallocation at some point. So the question is, where do we do it? Do we do it in the sender or on the receiver side? And also, at which point can we safely deallocate the memory? And how do we deal with messages that are dropped or lost? So they don't reach the target, but we still need to consider them somehow. In general, the shared memory cleanup should happen in the sender because there might be multiple receivers or there might be no receivers. So, and if there's no receiver, then the sender has to clean up the memory. But in order to clean up the memory in a proper way, we need to make sure that it's not freed when it's still in use by some receivers. So we need to keep track of all the receivers of the message, and the receivers report back once they're done with the data. And once all receivers are done, we can then safely deallocate the data again. So this is basically a reference count across process boundaries. And since we sometimes drop messages in the Dora framework itself, for example, when the sender is much faster than the receiver, we also need to make sure that we notify the sender in this case that it should not wait for any of these messages because they never reach the target. So this needs to be considered as well. Yeah, and our implementation for this was that we just create a unique token for each message in the sender, and we used the Dora daemon to forward the message to receivers. This Dora daemon is kind of the communication hub for each local machine. And it's also responsible for keeping track of the different tokens and the pending receivers. And all receivers report back to the daemon once they're done with the message, identified by the token, and the daemons then, once all receivers are finished with the message, it notifies the sender that the memory can be cleaned up again. Yeah, it's worth noting that in our API, you don't need to deal with any of this, so this is handled transparently. So if you receive such a cleanup message, then the sender will, in the API, take care of doing the deallocation, so you don't need to do any manual steps for that. Yeah, and the reason for involving our Dora daemon in all of this is that we can do an optimization because we're also communicating with the daemon a lot, for example, for requesting the next message that is incoming. So we can bundle these tokens together with these messages. So we request the next input, and in this request, we also list all the tokens that are freed and no longer used. And this way, we can reduce the communication overhead. We also cache the freed shared memory regions in the sender and try to reuse them for the next message to prevent the deallocation and allocation overhead. Of course, this only works if the next message is the same size or smaller. And for small data, we send it directly over the TCP channel because the additional system calls required for mapping and unmapping the data would be larger. So we did a bit of benchmarking and decided at like below, I think, a page size, we can send it directly. And larger than that, we use the shared memory. We also plan some future optimizations that we haven't implemented yet. So one idea is to implement a larger, to allocate a larger shared memory region when sending out data, so that we increase the possibility of reuse. So even if the next message is larger, we might be able to reuse a prior allocation, because we can like keep track manually which chunks are freed, and if we have like a continuous chunk that is large enough, then we can reuse it. Of course, this requires some manual memory management, and it's not really clear if that is really faster, so we need to, of course, benchmark this before we implement it, or like after we implement the prototype. And another idea that we had is to cache the memory regions on the receiver side as well. So depending on the workload, it's often the case that the same sender sends the same type of message multiple times to the same receivers. So in this case, it might be possible to reuse the exact same memory region or prior memory region again for the next messages, and then we can just keep it cached in the receiver and avoid the mapping and unmapping. And we also have like a prototype implementation of using a shared memory queue instead of the TCP socket for sending the metadata, like the shared memory ID and the output ID and so on. And yeah, this way we try to avoid the latency overhead of TCP. And for signaling new data, we can use native operating system events, and then we can, yeah, like use a normal single producer, single consumer queue in shared memory, which is thread safe and can be used by both processes at the same time. And this way we can hopefully speed things up even more. Yeah, let's go to let's talk about zero copy between Rust and Python. As we already saw a few times today, we have the nice Py03 crate for interacting between, like across Python and Rust. So you can just import the crate, annotate your Rust structs with a few attributes. For example, we have this data attribute here, data struct here, which is annotated with PyClass. This makes this struct available to Python. And we have an extract data function that takes reference to the data struct and converts the wrapped byte vector to a Python byte array. So it makes it like compatible with Python. And then we can call it from Python by first getting the data object from somewhere and then calling extract data to convert it to a Python bytes type. Unfortunately, this step is copying the data. So we now, after this extract data call, have two copies of the data. One is still living in data, and the other one is a Python variant of the same data living in bytes. And yeah, for large data, this can have some considerable overhead, so we want to avoid this if possible. The fundamental issue is that the standard Python types assume that the memory is owned by the Python garbage collector. So the garbage collector is typically responsible for freeing memory when the data is no longer needed. And the standard Python types are kind of hard-coded to use this garbage collector. So it's not possible to use zero copy together with the standard Python types. So instead, we need to go through the CFFI bindings of Python. So the idea is that we let the Python garbage collection only own a pointer. And then we can access it through some custom access methods, which use FFI calls to read out data, for example, directly from the original shared memory region. And once this pointer is freed, we want the Python garbage collector to invoke like a callback function of our FFI implementation so that the Rust or C code can do the actual deallocation of the data. And as you can imagine, this is all quite complex, so implementing something like this and ensuring that you're doing everything correct and not messing up some frees or pointers or something is quite difficult. So fortunately, we have the Apache Arrow project that was already mentioned before that implements something like this. So it specifically targets zero copy data sharing across different languages. So the idea is that it defines a format of data in memory that can be used from Python, from Rust, from C, and other languages without copying the data. So we have official bindings for both Python and Rust, which makes this very easy. And yeah, we have a support for higher level types too. The basic type of arrow is an array, which can be backed by multiple memory buffers underneath. And arrays can also have like child data to allow creating or representing more complex data. So for example, you can represent an array of byte vectors as like an offsets buffer and a child byte array, which contains all the data, and the offset buffer just contains the start index of each of the byte arrays. We'll see an example in a moment. And yeah, for Python interoperation, it's important that you can convert this directly to NumPy or Pandas. So for example, here we can see how to convert the NumPy array to an arrow array using pyarrow.array call. And the other direction works as well. And most importantly, converting it this way doesn't copy the data at all. So to understand how this works, let's look at the layout of this example array here. So we have an array of structs here. And the structs all have a string field and an integer field. The first entry has the string go and the integer field 1. The second entry has the string empty string and the integer 2. And the third entry has the string sim and the integer 4. And the representation of this is shown below. So we see the length is 3. So we store for each array, we store length as a metadata. And then we have like an array of buffers. In this case, we don't use any of those because structs in Arrow are represented using the children array. And the idea is that each of the fields is placed in a different array. So the first array contains all the first fields and the second array contains all the second fields. And here we also see how this offset buffer and value buffer works. So the value buffer just stores all the bytes continuously of the strings. And the offset buffer contains the start offsets of each sub string. So the first string starts at index 0 and goes until index 2. The second string starts at offset 2 and goes until offset 2, so it's the empty string. And the last one starts at offset 2 and goes until offset 5, so it's the string sim. In this way we can read the data out and interpret it. And the second array is just a simple array of length 3 and a value buffer with the integer values. And one of the reasons for representing the data this way is that you can do lots of operations on that data without the need to copy the data. For example, you could just remove the first element, and then you can just shorten the buffers or adjust the indexes, and you don't need to actually copy the data somewhere else. You can still point to the same original array. And using this arrow array implementation makes it possible to pass data from Rust to Python without any copying. So we do it in the following way for byte arrays. So this is the simple case. We first create a buffer based on the shared memory region that we received and use an unsafe block to convert that shared memory region into an arrow buffer. So we just consider the whole thing as a buffer. And then using that buffer, we construct an array data instance based on this buffer and give it the type byte array. And then we can use the official toPy object, toPy arrow trait to convert it underneath it does first convert it to a FFI compatible struct and then invokes the pyarrow implementation on the Python side to import that struct again, which doesn't contain any data, it just contains pointers. And then we can return this py object back to the Python node, and the Python node can then use the functions of pyarrow to access that data through the pointers that are stored. Or we can convert it to NumPy or a pandas data frame, and also there's no copy, so it's also based on FFI pointers then. And putting things together, we can see that this makes it possible to be much faster than Rust2 here, because our node is written in Python and Rust2 doesn't support zero-copy messaging for Python, but we do. So this allows us to pass data very efficiently from Rust to Python and from Python to another Python node and so on. Yeah, and that's the end of my talk. Thank you for listening.